my name is Patricia Dunlevy, and this is my Lab 9 for Physics 2211. The main objective of this lab was to model a spring's motion using VPython in 2 dimensions for comparison to an experimental video of a spring. And the main result was that while the experimental and model data matched closely, the match is not perfect because the system is a chaotic system. So I first updated the code that was given to us in lab by updating the mass based on what was given to us, and updating the initial position of the ball or the mass based on my tracker data. And then I kept my spring constant the same as I used in the lab, and the relaxed length the same as in the lab, because the spring is the same one used in the at-home lab or the at-lab lab. Then to model the motion of the mass, I used the total force acting on the mass, which in this case is the sum of the gravitational force and the spring force. So I found the gravitational force by using the ball's mass times gravity in the negative y direction, and then found the spring force to be negative ks times s, the stretch, times l hat, which is the direction vector. And then I used this information using the momentum principle to update the position of the ball. So then when I ran the model, you can see here my comparison of the model data to my experimental data. The model data is the red and the experimental data is the green. This is for the x position and this is for the y position. So as you can see, the graphs are pretty close, but they are not perfectly matched because the system is very sensitive to initial conditions. So having just slightly different initial conditions will greatly change the results of the model, which is why the graphs don't match up perfectly. So then I used the data from both Tracker and VPython to find the period of oscillation of each graph. So for the x graphs, for the experiment, I found the period of oscillation to be about 1.65 seconds, and for the model, I found the period of oscillation to be about 1.67 seconds, and for the y position, for the experiment, I found the oscillation to be about 1.52 seconds, and for the model to be about 1.50 seconds. And again, these differences in period of oscillation are probably due to the sensitive nature of the system and different starting conditions. Then I used VPython to calculate the energies of the system. In this system, which we are now defining as the spring, the mass, and the earth, there is gravitational potential energy, kinetic energy, and spring potential energy. So I initialized all these values by setting initially the gravitational potential energy equal to the mass of the ball times gravity times Paul's y position or height. The kinetic energy is 0 because we're modeling from directly the second after the spring, immediately after the spring leaves the hand, or the mass leaves the person's hand, so it's 0. And then the spring potential energy is half times k times the stretch of the ball squared. And then I updated this within the loop by using these same formulas for gravitational potential energy and spring potential energy, but adding in the kinetic energy formula of 1/2 times the ball's mass times the magnitude of the ball's velocity squared. So these 3 formulas together, and then I updated by graphing the delta of each of these energies, so the change in each of these energies over one time period, which is 1/210 seconds. And here you can see what I got when I ran the module and plotted the graphs of all the energies. The red graph is the kinetic energy, the green is the gravitational potential energy, and the blue is the spring potential energy. For the first what does it mean question, the x period and the y period of oscillation that I found were different, but only by about 0.1 to 0.2 seconds. And I think this might be because of the center of mass is different with regards to the x direction than with regards to the y direction, because the period of oscillation is dependent only upon the mass and the spring constant, and the spring constant is obviously constant for both the x and y direction. And for the second what does it mean question, in this case the system is the spring, the mass, and the earth. And in this case the work done by the surroundings is 0, and this is because the change in energy, it works with the energy principle, or this is consistent with the energy principle, because the total energy change in energy is 0. And here you can see my graph of the total change in energy, and while it looks like it is not 0, if you look at the values, you can see that in fact these values are very, very small, times 10 to the negative fifth. So they are virtually zero, and this probably just comes from rounding error in the way that the computer solves the problem. So we know that the total energy or the work done by the surroundings is zero because the change in energy is also zero, and because there is nothing else to acting upon the system when the Earth, spring, and mass are included. And finally, for the third what does it mean question, I changed the origin of the spring system, making the attachment point not the origin. So by the definition they gave us, the attachment point will now be at a height LO plus mg over k, which I found to be about 0.68857, and I put that in here. And then the initial ball y position will now be 0, because we wanted it to start at a y position of 0. So when this change of origin affects the physics of the system by making the initial gravitational potential energy 0, because the ball is at a height 0. And since the kinetic energy was always initially 0, this means that the spring potential energy will be 0 too, because the total change in energy is 0. So this, when I ran the graph of that, you can see that the graph pretty much just floats along at 0, because now the change in energy, changing the origin, has made the change in energy different, and now it's virtually 0.